Here is the diagram for units of knowledge that we try to combine together, and numbers here are different because we did the manual earlier. So I'll try my best to fit in 2 lectures, but maybe it will take one more. So by now we have learned concept of Slater determinant and spin that helps it. Then we were discussing the concept of mean field and variational theorem, and today we need to use concept of Slater determinant to separate repulsion, to separate interaction of 2 electrons on 2 qualitatively different components. And this concept that we slightly started on the previous lecture, and I'll repeat it, does not have analogy in classical physics, classical science, and it is not interpretable by visual concepts. It's a more abstract thing, but it is important for our subject. So interaction between 2 electrons just through equations will be chopped on 2 qualitatively different categories, which will be called Coulomb exchange. And after we admit presence of these 2 concepts, we will merge them with concepts that we learned before, mean field and variational theorem, and then together they will form the overall Hartree-Fock theory. So I plan to share, maybe suggest some pages from textbooks, and there are multiple textbooks and websites that summarize Hartree-Fock theory in half page or in 1 page. So after our 5 or whatever lectures on Hartree-Fock, you will be experts and you will be able to explain it to anyone else with a big confidence. So we intentionally slow down on underlying concepts so that later on you will be very, very confident. So I'll skip stuff that we did previously. Yeah, just maybe I'll repeat. I will give a little tour over these concepts on Friday to go over them. So last thing we did was variational theorem, and then we did consider composition of molecular orbitals out of atomic orbitals. And then we discussed that Hartree-Fock theory will be modifying expansion coefficients for expanding molecular over atomic until we minimize total energy. So here is the thing we did, the last thing we were discussing last time. So we were evaluating matrix element of electron-electron interaction in the brackets as a matrix element in the as expectation value of the Slater determinant, right? So and we did it only for 2 electrons and 2 states. So due to principle of antisymmetry, the Slater determinants do have minus sign in between. And we were decomposing this matrix element on 2 types just by opening these brackets. So we have 2 terms in first bracket, 1 term in between, and 2 terms in the second bracket. 2 by 2 will be totally 4 terms, and 2 of them that multiply plus and plus and minus will have overall plus sign, and two of them cross terms that multiply plus by minus and minus by plus will have minus sign. So those are two qualitatively different contributions to electron-electron interaction. And those with plus sign correspond to positive energy, which means repulsion. Those with minus sign correspond to negative energy, which corresponds attraction. So when energy of some object is small, or better, negative, it means object is stable. So due to presence of these negative terms, the molecules are stabilized. Do you remember this discussion a week ago? Okay. So I understand and appreciate that this discussion may bring all of us out of comfort zone. This is too many equations and too many abstract concepts. And it is not only for wet chemistry experts or polymer scientists. Even for professional theorists, writing long equation like this is a challenge. And there was a scientist in the community who was trying to address this challenge to make life simpler. And basically what he did, so the name is Richard Feynman, he got Nobel Prize, and he was also popularizing the science in several books. So his main contribution to science was that he introduced a way to convert long equations into small figures. So if you look into Wikipedia, into so-called Feynman diagrams, you will see these pictures like that. And these pictures are designed by professional theorist Richard Feynman to avoid writing long equations. So we all were kids, and we all were doing little drawings, and drawings can be intuitively processed much easier than equations. So the drawings with these arrows and wavy lines are suggested language to replace equations like we were analyzing 3 minutes ago, that may introduce a little discomfort. So let me repeat these two terms and slowly discuss how they are converted into pictures. So just in case you feel very discomfortable with equations, do not worry. The main goal of the course are practical skills that we do in the labs. So if you miss something, first, you can stop me and request additional explanations. Second, the equations are needed only to grasp the main concepts and get basic understanding what is being computed. But it is not a theoretical course, and there will be no exam on deriving equations. So you shouldn't worry much. It's more just to see the general trends. So matrix, we will discuss matrix element of electron to electron interaction with Slater determinant for two electrons. There are two types of terms. One term with plus sign and another term with minus sign. So if you are very carefully tracking what we are doing, you can see how these equations are, these two equations are derived. Before, we had matrix element with brackets, two terms in first bracket two terms in second bracket, Coulomb in between, and then we are opening the brackets. 2 by 2 is 4. And here we are given examples of two of these four terms. I'm writing only two because remaining two terms will repeat the same pattern. So when both terms do have positive sign, we observe that, you see, number of orbital and number of electron coincide. Number of, yes?
No. It's okay, Professor.
Okay. Number of electron, number 2, and number of electron coincide, right? And then if you compare thing with star and without star, it also completely repeats itself. So we have phi1 r1, phi1 r1. In the second factor in the product, phi2 r2, phi2 r2, right? So this term is simple and not challenging. Let me know if I need to speak more about it. No.
No, it will be better if you speak more.
Okay.
I can understand phi one star it's like, if I consider it like a multiplication, phi1 star with phi1 r, then phi2 star multiply with phi2. But why?
So,
Then,
yes. So this part originates from bra, and this part originates from ket. So the part with stars originates from bra, part without star originates from ket. And just by algebra, by opening the brackets for later determinant, we see that the greenish and yellowish thing coincide, right? Now, here are the rules of Feynman. Well, not all, but part of them. So we can consider this matrix element in the following interpretation. So we look on the wave function phi1 before interaction here.
okay.
Then it practices interaction, which is symbolized by maybe use pink, by Coulomb matrix element. And after interaction, it still remains a function phi1 for first electron, but with star. So the greenish thing is here, and the pink corresponds, this wavy line corresponds to this Coulombic interaction. So the arrows, straight lines and arrow correspond to wave function before and after interaction. Before electrons like collide and repel from each other. Now, by the analogy, if you look the phi2 before interaction and phi2 after interaction, right?
Okay. So, Professor, for phi1, arrow sign is like just go like inside, but for phi2, why arrow sign go outside? The arrow sign.
First, I can make errors. I can be there could be error on my side. Second, let me think. according to my own logic, there should be star should be in a different place. Maybe I'm missing something myself, but pure yellow color. Yes, I will double check and let you know if I'm making an additional error. But thank you, Kia, for a good eye. For me, it seems more logical this way as well.
Okay.
So we do have wave functions phi1 and phi2 before interaction, and the interaction happens in the points of space R1 and R2. So it is arguments of the arguments of this wave functions. So this can be interpreted this way, so that electron first electron in state 1 and second electron in state 2 collide with each other and then repel, and this diagram corresponds to energy of their repulsion. Make sense?
Yes.
So energy of repulsion and energy. And since it is positive sign, it is energy of repulsion. It's positive. Repel. Now let's focus on the second part of this slide. So since we have minus sign, it will be attraction. The energy is minimalistic, minimal attract, and it is very unusual situation. This term looks like two negatively charged electrons attract to each other. It sounds like a nonsense, right? But this is only abstract concept. In fact, all the time, both terms cooperatively describe electron-electron interaction. Just there are two mathematical terms. One corresponds is analogous to repulsion. Another is analogous to attraction. So let's look how the diagram will change if we look carefully translate this one. So we have phi1, phi1. Then we have phi2, phi2. But here it is interesting. In the bra part, the number of electron and number of orbital coincide for first and second. But in the cat part, they do not coincide. So basically, first electron is taking the second state, and second electron is taking the second electron takes first state, and first electron takes second state. So it looks like electrons did swap their state. And this is quite counterintuitive thing. So before interaction, we have first electron in state 1, and after interaction, we do not have its reflection as we had in previous diagram, but they, so to say, bypass each other. They exchange their order, and after interaction, we have
Why they exchange the order? Like it's like dump of energy.
So the only objective mathematical thing are those two red arrows. So when we open brackets in the Slater determinant, we observe that there is a term where states are swapped. It's just algebraic effect.
Okay.
And now we are trying to bring it closer to human perception, to convert this algebraic observation into something that we can interpret. So here at site 1, instead of electron number 1, we have electron number 2. And here at site 2, we have electron 1 instead 2. So in this bypass symbol, they are swapping their order. So if, well, I know that we, in our rest of our life, we will try to avoid equations and diagrams at all. But if by some reason one needs to discuss, yeah, I see there's Kay, your question. I will address it in a second.
The positive part, I'm able to understand clearly because you explained well. You also explained well this part, but
let me finish the sentence and then I'll go further.
Okay.
So the graphical representation of the second diagram will include this bypassing of lines, because orbitals are swapping their energies. It's just a convention. And sometimes instead of writing long equations, people are doing just drawing diagrams. By convention, there is a way how to perform mathematical operations without writing equations, just drawing diagrams. And then only the final answer is converted back into equation. So I see there was a question of Kia. How come this negative term and swap of orbitals appear? So let me bring back the source of this equation. So here is the equation that generates this result. So if I'm in first bracket, I have terms 1, 2. In second bracket, I have 3 and 4, right? Now, the result of overall equation will include 1 times 3, 1 times 4, 2 times 3, 2 times 4, right? So 1 times 3 will have positive sign. 1 times 4 will have negative sign. 2 times 3 will have negative because it's minus times plus, and 2 times 4 will have positive. Okay?
Yes.
Now if we focus on the term 1 times 4, Lina, there was a question from Kea to repeat where this negative energy comes from. I did return back a few slides. So if you look on this 1 times 4, and if you carefully track all elements.
I had a disconnection.
Okay, that's fine. Fine.
The question. Can you repeat the question, please?
The question is explain again the full thing for the negative one. So here is asking to explain where the negative comes from. So if you look on this 1 times 4, we see here we have first, and here we have first and second, right?
Yeah.
And here is second, and here is the second and first. So just by carefully practicing Slater determinant, we arrive to the terms where electrons swap their states and minus sign appears in the front. So it's just pure algebraic effect. And it is symbolized by this diagram. Okay. Feel free to stop me and ask questions. If it is boring or you are not interested, you can just lean back and relax and watch me trying to explain it. Yes?
Another question. Though you already explained this thing, for phi 1, it's like when it enter to in the electron 1 means electron 1, then it's turned to phi 2.
Okay, I understand your question. Whatever is on the left is electron 1, whatever is on the right is electron 2.
Yes.
So the line corresponds to the state, and position in space corresponds to number of electrons, to index of electrons. So now let me go further. We need to combine this concept of negative attractive energy with concept of mean field. So when we were practicing partial integration, not over all degrees of freedom, but only part of degrees of freedom. So if our multi-electron wave function corresponds to one electron wave function, we may want to perform not the full evaluation of the electron-electron interaction, but partial. So we may want to practice integration only over one coordinate instead of both. So I know it is very easy to get lost in these equations. So originally, when we considered full matrix element, we had integration over R1 and R2, right? So the full matrix element includes convolution over states of both electrons. And when we were practicing mean field, if your memory is visual, you may remember this ugly equation. We were practicing average over state of second electron. Now we want to combine this positive and negative contributions to electron-electron interaction and partial averaging. So only about one variable. So we can place everything that relates to second electron and just construct a thing that will have things related to second electron as new partial operator, and everything else will be away. So if I would be in the class, I wouldn't understand it and I would ask questions. Yeah, it is quite complicated concept. So I'm taking the first term and performing integration over R2 and focusing only on those things that depend on R2. So I take only the purple, only purple things. So integral of R2, this, and this, and I will call it J, which will depend on R1. Why I'm doing it? Because I need an equation that will act only on one electron. So currently, our electron-electron interaction depends on position of both first and second electrons. It's very bad operator mathematically. It implies that we need to have at least two electrons. And I want to solve equation only for one electron. So I need to do something with the second one. I need to remove it or make an average over the second electron. So if I take this purple stuff, I will remove second electron and make an equation that will act only on the first one. So here is this stuff. So integration over the, here is the purple thing. And the result of this integration will depend on R1, and it will be more normal, regular equation that will be possible to utilize in one electron consideration. So if you take the thing that we call J, we can take one electron matrix elements with the first electron, and after this second matrix element operation, we will get numbers. We will get actual matrix element. So if you do second integration over another variable R1. So this was for repulsive part with a plus sign. Now I want to do the same thing for attractive part with the minus sign. So I will practice integration over R2 here, there, and there. I keep minus sign as we agree, but due to antisymmetry, the second electron is taken now state number 1. So in previous expression, we had the same electrons here and there, same orbitals. Now we have different orbitals. So electron number 2 decided that it wants to swap its orbital, to exchange its orbital. And this term will be negative contribution to this partial hybrid, partial operator that will act only on one electron. So it's quite normal if by now you feel great confusion. I will try my best to resolve it, both for me and for you. So let's try to use the graphical Feynman expressions for this partial integration. So if we do have this stuff that we call the symbol J, purple stuff, second electron orbital 2, second electron orbital 2. So this purple stuff is able to act as an operator on the first electron. So here is my favorite part that I'll draw right now. So this purple integration over the state of second electron in this Coulomb thing means that we just cover everything that relates to the second electron by a box. Here I did it by purple, and on the next slide I do it with black box. So in some sense, electron number 1 is practicing reflection from the black box. So this term J1 is a structureless black box from which electron number 1 is reflecting. Please tell me if it looks more or less okay, or if you're completely unhappy with this. Just give me some signs so that I either go forward. Okay. So I need to match several concepts. One concept is Slater determinant and plus and minus contributions to the total to the energy on one hand. On another hand, I want to derive equations that will deal only with one electron. So I want to match 2 electron consideration and 1 electron consideration at once. So in order to get rid of the second electron, I perform this integration over coordinate of second electron. Okay? And if I perform this partial integration, the resulting object will be matrix, will be a number in respect to second electron, but will be still an operator in respect to electron number 1. So this operator in respect to operator for electron number 1. So this operator for electron number 1 will be structureless object that reflects electron number 1. So this is electron number 1 before interaction. This is electron number 1 after interaction. And we know that this interaction originates from electron number 2. But we want to remove any memories about electron number 2 from explicit consideration. We want to store, to save average information about electron 2 just in one object. Is it better? Okay. And this was only for positive part. Now, if you want to practice the same thing for okay, I believe a couple of years ago I tried to do it in a pictographic way. So how the electron number 1 is transformed by this operation and it changes its shape. But I'm not sure if it is helpful. So now we need to treat the second type of terms, which is negative. The diagram where electrons swap their states. So I still want to practice integration over the second electron. And I still want to act on the electron number 1, which is now in the second state. But after practicing this operation, and here is the confusion for everyone, after practicing this operation, which we put in this symbol K, the electron number 1 goes from state 2 to state 1. So in order to practice this thing, we need to observe this swap of the electrons, swap of the state. So if you feel confusion at this point, it is normal. I feel this confusion for last 25 years. But the summary was the black box, and before interaction, the first electron is in state 1. After interaction, it's already in the state 2. So there is a black box that induces change of state of an electron. Or instead of change, I would use the word exchange. So by this additional term, electrons are swapping, exchanging. And this term has negative sign. But the only good thing that I want to admit, that this object, although it is quite crazy, this object K is one electron operator. So it's operator for one electron. One electron. And a couple of years ago, I was trying to formulate and show graphically how it acts, but again, this graphical thing may not help in getting the concept. So these abstract things are important part of developing equations that are being solved in modeling of materials. Whether we accept or reject it, whether we agree or disagree with it, it was already used by human society to derive theories and program them into the software that we are running, like Hartree-Fock in Gaussian. And those people who were using it were designing also shorthand notation for these two electron integrals. So to avoid writing this denominator with R1 and R2, they were using brackets. And if the indices instead of first and second states are labels with leading indices, let's say RSTU, they use this notation with curly brackets RSTU. So please do not try to memorize it, because I will not be able to check it because I'm not using this notation. But if indices before and after vertical line coincide, like 1, 1, 2, 2, it will be Coulomb. Repulsion is plus. If indices before and after are swapped, it will be exchanged, which is minus. So in previous years, we were finishing lecture at this point, but I suggest we go a little bit further. And it may sound adverse and challenging to heal one confusing material with another one, but if you see the whole picture, maybe it will be less confusing. So, Hartree did mean field approach. So he got rid of all but one electron, but he did forgot about the term with minus sign. The Vladimir Fock contributed an idea to use this minus term, which made things to work quite more reasonable and make more to predict molecules to be more stable. So here is part of electron-electron interaction which corresponds to repulsion. Here is one for attraction. So we are going to practice an equation that we were discussing more than a week ago. Let me show this template equation. Yep, this one. Where the terms here, so it's one electron equation. Right now, it includes only positive term. Okay? And due to our consideration of antisymmetry, we will use minus term, minus k. So this is the main idea. So we add minus term into one minus energy, negative contribution to electron-electron interaction to equation for one electron. Whew. I'm going to speak something more, but this probably is most important part of our today's meeting. And it was why we were sacrificing our intellectual effort and time. So all this consideration of Slater determinant and these strange diagrams were needed to justify that we will add negative term into the one electron equation. So please ask question or show satisfaction or dissatisfaction with this main idea. We add negative term to one electron equation. Okay? And now confusing and adverse things start to finish. From now on, things are going to be a little bit more natural and intuitively understandable. So this thing, phi1, for which this equation is designed, will be a molecular orbital that you were drawing in the homeworks, right? So this is actual equation for molecular orbitals. The equation for molecular orbitals that includes negative exchange term is named Fock equation. Because due to Fock, we add this stabilizing term. But from now on, we are coming into constructive stage of discussing details of the equation to develop molecular, to find molecular orbitals. Okay? And I will speak maybe about a couple of slides more, but we will be in much better stage towards continuation. So for molecular orbitals, we need to use linear combination of atomic orbitals, right? You remember this. So right now, we are coming to new subsection. So if we really want to do computation of real molecules, we need explicitly process this summation. We need to select basis functions. We need to select how we will represent atomic orbitals. And it is the subject that was presented by Kea and Lina, right? On Friday.
Yeah.
So before we define atomic orbitals, we cannot go further to solve equation for molecular orbitals, right? So a very, very brief summary about basis set and orbitals. So if you look only in one dimension, so atomic orbitals, probably instead of, yeah, I'll still draw. So if you have center of atom, R1, and position of electron, lowercase r1. For s orbital, maximum is at the center of atom, and then it exponentially decreases, right? If it is, so it is s orbital. If it is p orbital for ion 1, then it is 0 near the atom, and then it decreases as we go away. And it changes the sign, right? Plus and minus. So it is one-dimensional representation of the you have seen it, like p orbitals on oxygen, right? When we were drawing orbitals, so plus and minus. So these mathematical expressions, these sharp cusps, give a lot of problems to anyone who will try to find two electron integrals, to anyone who will try to find Coulomb and exchange integrals. And therefore, there is a quite cheesy approximation. Instead of this absolute value, one puts just square, which looks mathematically wrong, right? It's two different functions. But if we explore these functions quite far from the center, the Gaussian function and this absolute value function will be relatively similar. So Gaussian function and atomic function will be similar on the ranges away from center of atom. So in very, very oversimplified way, the Gaussian software is based on this approximation, on using Gaussian type basis set. When atomic type orbitals replaced by Gaussian function. Okay? So if you disagree or have questions, ask Kia and Lina. Now they know more than I do about basis set. In preparation to our future life in the course, I want to bring you up that in addition to these atomic centered orbitals, there are also plane waves, which are continuously distributed everywhere, not only in vicinity of atom, but everywhere. Okay, and I think about now we should finish, but then we will be able to do a good job when we meet on Friday. So in order to define molecular orbital for which we will have Fock equation, we will use specific atomic orbitals. And then this general expansion of molecular orbitals over atomic orbitals will be plugged in. I'm going again back and back again. Will be plugged into Fock equation. And as a result of plugging in, we will find out the set of expansion coefficients of molecular orbitals over atomic orbitals. Whew. I suggest we should finish at this spot. So let me know if if you want me to comment on something or if there are questions. We are a little bit over time, but I'll share the recordings. But on my own assessment, I think we overcame most complicated part of this chapter, and things should become more intuitive and understandable. Whew. I didn't achieve the end of the distributed slides, but with your permission, I suggest we finish here. If no one pushes me to continue. So if you want summary, oh, I may have forgotten to highlight the names. So positive term in the energy is called direct Coulomb or simple Coulomb, and the negative part is referred to as exchange. And it is a terminology that if you read literature or talk to professionals in this area, you tell that my equations include both Coulomb and exchange. And people will say, oh yeah, okay, molecules will be stable. So today we did a again come back to the list, to this flowchart diagram to see where we are in this discussion. So today we have discussed how one gets Coulomb and exchange terms that originate from Slater's determinant, and then we did partial integration over second electron, and we got J minus K one electron operators that form Fock operator. This knowledge plus variational theorem will be combined together on our next meeting, and it will give the full picture of how Hartree-Fock method is working. If you are curious, it will be to some extent quite similar to the algorithm for geometry optimization. Remember, as we were playing with our robots and we were trying to find minimum of the parabola. So I'll leave this intrigue to the next time, but you will see another. Enough. I'm done, and I will not offer new information unless anyone asks questions. So many thanks for investing your time and effort. And I believe we have completed all challenging parts of the course. So everything we will cover later will be less challenging. So I'm congratulating you with completing this milestone. So I see that no one wants to disconnect. So maybe you have energy for more discussion. Let me check how. I'm pleased. Maybe let me check how you did interpret what we covered today. So Lola, will you share your impression? Do not worry. Just share how you understood what we discussed.
Okay. So according to the equation, there are 2 electrons, but we need just 1. So we're trying to use the concept of Slater determinant to eject 1 so we can keep 1. So yes, I guess that's all what the equation and modification using the exchange and direct Coulomb effect, just to try to delete 1 and keep 1, basically. Okay.
So which one has negative sign, Coulomb or exchange?
Exchange.
Perfect. Yeah, very good, very good. I think you got the concept. I'm happy. Thank you. Steven, would you like to share your summary, or your impression of today's material?
I can try. Yes.
Please.
So this is the whole lesson? Right. So when working with simplifying electron calculations, you have to calculate that when two electrons interact, they don't just have a singular force acting on them. They also repel each other as well as attract each other, was my understanding. No?
Yes, yes. You are mathematically correct, but what is the reason for this attraction? And the question is very challenging. I would be challenged to answer it myself. So you can answer either mathematically or intuitively.
Well, the first thing that just comes to mind is gravity, but that doesn't sound right. But it's, I don't have something to write on. I feel like I could explain it better that way. The lowest energy state is when they'd be touching each other, but that can't happen because they have energy and are repelling each other away.
Mm-hmm. So how does it connect it to antisymmetry, to requirement of antisymmetry of multi-electron wave function?
I'm not sure.
But you are going into right direction, so the two electrons cannot occupy the same state, right? Which drives us to Pauli exclusion principle, and further drives us to antisymmetry of electronic multi-electron wave function. And this attractive term in the electron-electron interaction is a mathematical consequence of antisymmetry of wave function, and in turn of Pauli exclusion principle, and in turn of the impossibility for two electrons stay the same state. Okay?
Yes.
Thank you. Sarah, would you like to share your feedback or your impression of the materials we discussed today?
Thank you. At first, thank you for the nice lecture.
Thank you. I'm not sure if it was nice because I was reading from your faces that everyone was not sure.
Of course, it was complicated for me, at least because I don't have any background in the chemistry and physics. But at least I have learned the direct or Coulomb for the positive and the exchange for the negative sign. So that would be very helpful for me when I read an article or paper regarding the quantum.
Okay. Okay.
Yeah, thank you. And I just get it that it's a kind of simplification for the interaction between two electrons that we simplified to just considering one electron and then writing some equation to calculate that energy.
Excellent, excellent. Yeah, thank you. Thank you. Lina? Thank you, Sarah. Lina, would you like to share your impression or vision? What was interesting or what was boring, what was clear or unclear? Or
it was it was interesting for me because going through how to get a contribution of the more parts of the electron-electron interactions, such as the exchange part today. So it will give it gives better understanding, like how these functions can work for solving our models, and also how to combine these two parts, like the Coulomb one, as we always know that each two charged particles could have in the atomic system will have repulsion and attraction part. So giving in the, like I get connected the how to express these two concepts in the equation, how to apply that in Schrödinger equation, working more on the energy, total energy part by adding these two parts for the electron-electron interaction. So yeah, I think it gave me like a better understanding about solving our model.
Okay, yeah, thank you. And we didn't hear Kia. Would you please summarize your vision of today's material?
Okay, in today's lecture, actually, you discuss so many things, and like you are saying that Coulomb and you just said that Coulomb and X in their exchange term, Coulomb is like positive and exchange like negative term. So using those terms, you are trying to explain the molecular orbital which carries the signature of the electron-electron interaction. And another thing is that you want because if you use two electrons, that result will maybe give you it will take time. No, it's not a take time. It will give a wrong result. That's why you want to remove the second one, and for that you showed a equation, bunch of equations J R like this. So that one so you want to show one equation only for one electron, then we'll able to get a result from that only one electron.
Excellent.
There are so many things also. I need to read.
No, thank you, and you highlighted an important aspect that most of the class attendees were focusing on the Coulomb exchange, and you did put an accent on the average over other electrons and focusing on one electron. So everyone was mentioning it, but you highlighted it. So we are trying to balance between several concepts, and this concept of Coulomb exchange originate from Slater determinant and antisymmetry, as we discussed with Stephen, and the wish and attempt to consolidate everything into equation for one electron comes, that Kay highlighted, comes from the concept of mean field.
Yes.
That all but one electrons create a distribution of charge in space, and this charge exert Coulombic force on our selected electron. But due to antisymmetry, this Coulombic force will have not only attractive but also not only repulsive but also attractive term. Good. I think it is the first time in all years when we had such discussion at the end of lecture, and I think it is the best part. Thank you for suggesting it, or thank you for giving chance to have it. It's great.
Dr. Kellen, did you read my email regarding the homework?
Email about homework? Yeah, the answer is positive.
Okay.
I'll answer by email, but the answer is positive.
Okay. Thank you.
Okay. I do not have any other items in the program. So of course I will be happy to deliver more material, but it will be much more healthier than we digest information and take next chunk when we meet next time.
Maybe today no one wants to leave this class.
It's a big surprise for me. I thought everyone will seek an opportunity to like disconnect and leave as soon as possible because it was larger amount of material than usual. But thank you for staying longer. I am pleased and touched. Just for the sake of successful progress in the class, we will limit amount of material maybe at this point and continue next lab tomorrow and virtual Friday.
Thank you.
Thank you all.
Have a good night. Bye.
Good night.
Good night. Thank you.
Good night. Thank you, Sam.